Okay, from our last lecture, we learned how to linearize the power system with many generators. For instance, for this three machine power system, if we model each generator by the classical model and we put all the equations, including swing equation and also power flows of the network together as the full differential equation model, we linearize each equation. At the equilibrium point, we'll have the standard state space representation of the linearized model. And from eigenvalues, we actually prove the rank of this A matrix is at most n m minus 1. If the total dimension of the A is m, so the rank of the matrix will be m minus 1. So there will be at least one eigenvalue which is 0. Which means there could be another real eigenvalue, but that indicates the total motion of the machines, but it's not concern of a small signal stability. So for such a system, it typically has I'm minus 1 oscillatory mode, which means I'm minus 1 pairs of a conjugate eigenvalue. So our stability analysis will focus on those n-1 oscillatory mode for small signal stability. Depending on the frequencies of those oscillatory modes, we can categorize those modes into three types. The first one has slower frequency, so usually it's lower than 0.7 hertz. We call it inter-area mode or intra-area mode. Inter-area mode means there are two areas oscillating against each other. Because the two areas can be far from each other, connected through long transmission paths, so the frequency is slow. The frequency actually can be estimated based on the single machine infinity bar system. If you can generate equivalent single machine infinity bar system, you actually can utilize the total inertia of the generator and also the readiness of the transmission path. You can estimate the frequency. So finally, you'll be able to see if the two areas are really far from each other, the frequency will always fall into this range, lower than 0.7 hertz. But if it's close to the 0.7 hertz, which means it can be a two group of generators within the same region but oscillating against each other. So anyway, the first type, you can simply consider it as inter-area mode. The second type is called the local mode. A local mode means the oscillation happened in one power plant. It can be one generator versus the rest of the power plant and the rest of the system, or maybe a two group of generators oscillating against each other within each power plant. Anyway, that's called the local mode. The last one is much faster. That is typically not very visible from the network, but it can be detected within the power plant. So that can happen with the controllers inside of each power plant. So after we finish today's lecture and we introduce two very important concepts, and we can use those two concepts to explain why we have three categories of modes. Okay. So the process to linearize a general power system with a lot of generators will be basically similar to what we have done for the three machine system with classic model. So first, our goal is to generalize the linearize the differential equation on the state variable, and also we linearize the power, equations on power flow. So we can use these two equations to represent the linearized version for each dynamic device. Then we can connect all the dynamic device into the system. We put the first equation, differential equation, in the first one, and we put all the algebra equations, the second one, into the second one. We will create much bigger equations. And also we can add the network model. So finally, we will create the linearized version of the entire system. So that system will be similar to this one. So here, we somehow solve the voltage from the linearized version of the power flow equation. and plug in that one into here to replace the voltage in the linearized model. And we can finally we can generate purely ODE model. So that will be our standard form for the linearized model. Okay, so this one, the A here include the linearized model for each device and also the network linearized equation from the network. From Quinter's book, there's more details to explain how this one can be done. But this one is not required. But we can understand if you use any commercial software to have a linearized version of the power system model, it actually goes through this process. So A here is not only from the dynamic model of the generators or other devices, also from the network. So network also become part of this A model. Then we find eigenvalues and other model information. We'll be able to study the oscillation for the entire network, not just for generator. Okay, so next we just go through basically same process as we use for single machine InfiniBus system. But first we have, this is a nonlinear model, and we generate a linearized version. In this linear version, in order to do that, we consider deviation from equilibrium point, okay? And then the A will be basically just Jacobian matrix for all the nonlinear functions used in the differential equation with respect to change of the state. And the change of the nonlinear function with respect to all the input will become a B. So B just model the input channels. And A just model the total linearized model of the entire system. Remembering for the single machine InfiniBus system, we solve the zero input and zero state responses. Then we combine them, that will give us a general solution of the state. So here we can do similarly, because now it's a linear model, the final response of the state vector will be a combination of one is a zero input, which means if there's no change on the U, only initial state in the state vector will cause some dynamics. And the second part is what if the initial state is staying at equilibrium, but we give some change on the input. So that will also cause some response. So together will give you more general response of the state variable. You can follow this process after generating the linearized model. You do the Laplace transform, and using from the frequency domain, you solve the state variable. Here is state vector, and then you do the inverse Laplace transform. You'll get time response of the state variable. Yeah, that basically same procedure. But what I'm going to talk about in the following is not going through this process. We're going to utilize eigenvalues, eigenvector to simplify this process, because our goal is now to obtain the final response. Definitely final response is also useful. If you know the response of the system following any disturbance due to any change of the input based on the waveform, you will know the system is stable or not. But here, we want to utilize the eigenvalue and also the eigenvector, right? Without solving the response explicitly, but we still know the stability and we can do some design. So that's what we want to focus on, okay? At first, I just gave you a big picture about all possible eigenvalues. So even here, we only focus on oscillatory modes, which means the complex eigenvalue, the conjugated pairs of complex eigenvalue. So if any eigenvalue is real, it corresponds to a non-oscillatory mode. Non-oscillatory mode means there's certain pattern of the system to move. So if you start from a state in the eigenspace of this eigenvalue, it will follow the exactly same pattern. But this pattern is not oscillatory, which means the dynamics projected to any coordinates of the state space will not be periodic. It will be basically just going into the same direction. So same direction means because here we assume that the real part to be non-zero, but the imaginary part to be zero. So real part either it's positive or negative would really tell the mode to be a decaying mode or maybe growing amplitude mode, okay, based on the sign of the sigma. So if you draw for a system with only just two eigenvalues, so if both eigenvalues are real, if it both on the left-hand side of the imaginary axis, so the mode will be stable. So which means if, in the state space, if you start from any initial point, if it's on the trajectory of one mode, it just follow that trajectory, go to the equilibrium. Okay, so it could be another trajectory, which is, for this case, there will be two separate independent trajectories. If both eigenvalue on the right-hand side of the imaginary axis, so you still see two trajectories, but direction is reversed. So if you start from any point, it will just become further from the equilibrium. The system becomes unstable. For the stable point, that is called stable node, or maybe stable equilibrium point. For the unstable mode, if both modes are unstable, so that equilibrium is called unstable node, or maybe unstable equilibrium point. A special case is one eigenvalue on the left and the other on the right. So which means in one direction, the amplitude tend to decrease, but the other direction, the amplitude tend to increase. So for instance, in the x direction, the amplitude tend to become closer to the origin, but in the y direction, the amplitude tend to become bigger in the amplitude. So finally, you will see the saddle point. Okay. So if the system has two conjugate complex eigenvalues, we already learned how to calculate the natural frequency and the damping ratio from the real and imaginary parts. So we also have three scenarios. The first one is both are stable on the left-hand side. So no matter how you start the state, so we'll always go back to the stable equilibrium point. And the second is both unstable on the right-hand side. So no matter where you start, it will always become further from the stable equilibrium point. And the last one is it's like marginally stable case. It's not unstable. It's exactly on the imaginary axis, which means if you start at any point, it will just stay on that orbit, okay, close orbit surrounding the center, the origin. The amplitude is bounded. It's not really unstable, but it can be a marginal condition, which means in practice, this is also bad because any perturbation will cause the instability of the system. So those are all the modes we have, but here we focus on those two possibilities. We want to check whether each oscillatory mode to be stable, unstable. Okay, so if it's unstable, we definitely need to do some control. If it's stable, if we want to make it even more stable, which means we can design the controller to push the complex eigenvalue to the left, further to the left. That will increase damping. That's what we want to work on in the next few slides. Okay, so next I'm going to talk about the method to solve the zero input response, not through the Lambda transform and the inverse Lambda transform. Because here we want to identify the modes of the system and understand the stability, and also we can discuss on any control design. So the approach is a modal analysis. Modal analysis basically means eigenanalysis using eigenvalue, eigenvectors. But I have to emphasize what I'm going to talk about for this modal analysis modal analysis approach is not new. So I assume you have already taken linear system or linear control theory class. So any conclusion, any formula here shouldn't be unfamiliar to you, right? You should be able to see similar conclusion, okay? So because we already have the linearized version of the power system, we just take this standard process to study the stability. So here we assume the model, here it is a power system, but the entire approach can be utilized to any dynamic system if we focus on the oscillatory modes. We assume there's an initial condition, and we have n eigenvalues. N eigenvalues here, we can just treat n as maybe even number. So n eigenvalue means you have n divided by 2 pairs of conjugate complex eigenvalues, right? But here we just call those eigenvalues as n modes. But you understand they appear as conjugate pairs, which means if lambda 1 and lambda 2 are conjugate pairs, lambda 1 carry all the information of lambda 2. Okay, you can call lambda 1, lambda 2 as 2 modes, but actually they represent the same oscillatory mode. Okay, so yeah, so I don't bother to define which one is whose conjugate. So let's just assume there's n eigenvalues. Okay, for each eigenvalue, if there's a row vector, they multiply A from the left-hand side, which is equal to the eigenvalue scaling this eigenvector, this vector. So we call this vector, we know it is eigenvector, right? That's definition of eigenvector. But because we assume this vector is raw vector, so we call it a left eigenvector. So usually we use the letter psi. Psi just means it's just a left eigenvector of ith eigenvalue. Similarly, you can have another column vector. Okay, that column vector multiplying A matrix from right-hand side, it also become the same eigenvector scaled by lambda. So this one is called the right eigenvector. So either it's left or right, really depending on it is multiplying the A matrix from the left-hand side or right-hand side. Okay, so left eigenvector will be a raw vector, and column vector will be a right eigenvector. So next, we can just put all the such columns for all eigenvalue together to form a matrix. So this matrix is a square matrix. For the matrix formed by right eigenvector or the column vector, so that one is called a modal matrix. So usually some papers they mention modal matrix really mean to find all the column eigenvectors, the right eigenvector to form this matrix. Definitely you can create another matrix with all the raw eigenvector. This is also considered a type of modal matrix, but usually just by default we call the capital phi as the modal matrix. Now this capital psi. Okay. So if the A matrix has all eigenvalues be different, so this can be easily true for any engineering system which is well designed. Because when you design an engineering system, you need to first avoid any resonance. Resonance, which means the system is not designed well. So one part is oscillating against the other part. Their modes will have some very simple relationship. For example, when you design the system, the mode 1 plus mode 2 will be equal to mode 3. Okay, so which means the system will resonating. So usually this one can be avoided. So if that's true, so the A matrix will have n linearly independent left eigenvector and n linearly independent right eigenvector. So this one just to make sure the phi matrix and the psi matrix here are non-singular. From the definition of eigenvector, okay, from this equation or that equation. So if we put those equations for all the eigenvectors together, we can quickly prove the matrix psi or phi diagonalize A into a diagonal matrix made by all eigenvalue, which is this one. Right, because that's very easy to prove. For example, from this one, if you put each psi I as a raw from a psi 1 to psi n, So that will left hand side will give you the total matrix psi, right? Multiplied by A. And the right hand side will be actually all the eigenvalue multiplied by psi. Then you can make this, move this one to the left hand side of the equation. You will have, this is what you prove on this part. Similarly, you can do the proof for the phi matrix. Okay, so next, if we compare this and that, it seems the psi is somehow related to inverse of phi. Okay, so which means even psi is different from phi. They're only different by maybe a scalar multiple, which means for each row of psi, you multiply by some number. Okay, then you solve the inverse. That can, by finding the proper scalar multiples, you will be able to get exactly the phi. So then we can simply just let psi be inverse of phi. Okay, so which means here we can first solve a right eigenvector for A matrix. Then we make all the right eigenvector to form this modal matrix. The modal matrix, then we solve the inverse. That will give us the left eigenvector, the right eigenvector. Okay. So that also had the conclusion: the left and right eigenvectors for different eigenvalue must be orthogonal. So if we do a proper normalization, if we pick any row, any left eigenvector, and any raw eigenvector, if they are associated with different eigenvalue, this product, because psi here is a raw vector, right? Phi is a column vector. So this product will be a scalar. The scalar must be either 1 or 0, depending on here, they are about the same mode or not. If they're about different modes, so those two vectors will be, the product will be 0. That is, the inner product will be 0. Otherwise, it will be some number. But if we do a normalization, such as we define psi to be a simply inverse of phi, so this one will be simply 1. Does those conclusions familiar to everyone? All right, okay, it's good. So okay, so next we're ready to find the zero input response of that S. We can utilize psi or phi here. Assume we know some initial condition, so the idea here is, because we have n modes, right, from lambda 1 to lambda n, and so if we observe the response of each state variable, so that one can have dynamics associated with all the eigenvalue. But if we can find any new coordinates on the state space, so we can find a set of decoupled state variable. We just call it from Z1 to Zn. And we hope the Z1 to Zn will correspond to lambda 1 to lambda n, respectively, which means so there will be a single differential equation for lambda I. So that one tells how the Zi will change if we know the initial state. So we don't have to worry about any other modes. So only each mode is linked to the single state variable Z. So here we can just call Zi itself as the mode I, because it's completely categorized how this mode can oscillate. But definitely we need to figure out how to get Z from a regional state space. Okay, so we make all the equation together. So now the linear equation is not A, become lambda. Lambda, capital lambda here is just diagonal matrix with all eigenvalues. And because we know that the lambda can be obtained by using this equation, okay? So we can just replace lambda by this expression using phi matrix to diagonalize A matrix. Immediately we can multiply both sides by the phi, so we'll have phi transforming the new state vector, the derivative of a new state vector. Right-hand side will be a multiplied by phi z. Okay, so if we compare this equation to the original equation, we know if the phi times z will be the response of the original state variable. So if we can find z and multiply by phi, that will give us the solution. That's exactly what we are looking for. But the condition is we need to know what z is. So this will be one way to solve the response of the original state variable. Similarly, we can, so that also gave us a formula to calculate z, because for this equation, if both sides multiply by inverse of phi, we'll have z is equal to a phi inverse multiplied by delta x, because phi inverse is basically just psi. So basically, which means if we know the matrix made by all the left eigenvector, all the raw vector eigenvector of the system, that one multiplying the state variable of original system will give us the new state variables, which are decoupled regarding all the modes. Then let's continue, okay? So next, we are going to replace each of them by this one, okay? Because each z depends on the initial amplitude multiplied by exponential function about regarding this lambda, this mode. So we'll have this one here. So now we only need to know what this Z0 is. Z0 just indicates the initial excitation of the mode or initial amplitude of the mode. So if we can solve this one, we know this value. Using this formula, we can directly calculate the response of the state variable. But here you see this equation already tell you one formula to estimate the initial excitation of each mode. So we just simply plug in t equals 0 to that equation, and we'll have this formula. So it tells if we know initial state of original state vector multiplied by the left eigenvector of mode I, you will have initial excitation of mode I. So now you plug in this one here, right? So finally, we have the final formula using the left or right eigenvector to solve the response. Okay, you don't need to go through the Laplace transform, inverse Laplace transform, but this one will tell the response. It will be exactly the same as the method from the previous slides. But here, we're not really looking for how the waveform look like. We really want to try to understand how those eigenvectors will influence the stability of the system. If you want to spell out for each state variable, so you can use this formula to calculate the response of each one. Right? Does it make sense? Clear? Okay. Let's move on. All right. So as I said, we already know the response, right? If you have a MATLAB code to program based on the formulas either from previous slides, maybe the one slides before, so you can calculate the exact response. By checking the response, you'll be able to know the mode is stable or not. So now the question is, what if the mode is not stable or the mode is not very stable? We want to find out some very useful information to understand maybe the shape of the mode, the composition of mode, and participation of the state variable in the mode. So we have to introduce three very useful concepts to categorize everything about this mode only from those eigenvectors. So we know delta S1 to delta Sn original state variable, right? Z1 to Zn a new state variable, but they each categorizing a mode. So we can simply call maybe Z1 as mode 1 or Zn as mode n. But basically we mean because that one really tell how the oscillation happened regarding that mode. From previous slides, we know the connection between the original state variable and new state variable will be using this modal matrix. transforming the z vector will have a regional state variable. So if you spell out this formula for each individual variable, that will be calculated by this expression. Because we can also move the phi matrix to the left-hand side, it will become the inverse. So that also tells you how you can transform a regional state variable to the new state variable by this formula. Next, we pick just single mode. That's one example. Let's just pick mode number 1, which means lambda 1 or Z1. We write down all the equations from here. Okay, so this equation tells the left-hand side equation will have the state vector. Right-hand side will be a modal matrix multiplying the vector of Z. If we color only the elements involving the mode 1, okay, definitely that mode 1 can appear in every single state variable in the regional space, which means every X you should be able to see mode 1 if that one really exists. But on the new state space, that only happened with first state variable. But how does that first state variable propagate to all entire system? Because that one need to multiply the first column of the modal matrix and to contribute to each of the regional state variable. The first column will be the right eigenvector of the first eigenvalue. So which means if we focus on just single mode, that mode has representations at all state variables. Okay, their representations really depend on what those phi elements are. So if that phi element is too large, which means this mode will have a bigger activity in the final state variable. If this phi is close to 0, so that mode is almost not visible from that state variable. If the Z because remember here, all the elements in the phi matrix complies, which they are not real, but they also each one may carry certain amplitude and angle. So if the first phi 11, and the phi 21 has opposite angle, so phi 11 has positive angle, phi 21 has negative angle, which means even for the same mode, they can be presented from two state variable totally different. One is moving up, the other moving down. So which means the phi 1 completely represent the shape of the mode. So that one is called the mode shape. Similarly, we can write down all the equations on how the state vector S can be transformed to Z. We will have this one. So this Z1 will be just first mode. Okay, but this vector is about all the state variables. So all the state variables multiplied by the element in this row will become the mode. So the second equation tells how is this mode formed from all the state variables. So all the state variables will have their contribution to this mode. All right. So the first equation tells about how each mode is presented in all state variables. The second equation tells how all state variables together form one mode. So we can call the second, that row vector, the psi 1, as the mode composition of mode 1. So we generalize such analysis to any mode, like mode I. So we define right eigenvector phi I as the mode shape. It just means so its case element, for example, phi ki, tells the activity of xk in mode I. So here I intentionally to use the index I for the index of mode, but use k, index k as the index of state variable. A left eigenvector psi I tells the mode composition of a mode I. Its case element, so here is basically just psi ik, because it's a raw vector, so k will be the second index. That one will measure the contribution of xk to the mode I. Okay. All right, so we can just simply define a new index, which is just product of element by element of that mode shape vector and mode composition vector. So for instance, the first element from the first vector and first element from the second vector, that will become the first index here. We call it just PIK or PKI. So that one, we call it participation factor. Participation factor, PKI, basically just the product of psi k multiplied by phi ki. Because phi ki means the k state variables activity in mode I, and multiplied by its contribution to mode I, which measure the two ways connections between a mode and the state. So that really tell the participation, real participation of the state variable into the mode. Okay, because it's a bidirectional participation, which means it's possible one state variable contribute a lot to a mode, which means if you get rid of this state variable, if this state variable from some generator, if you disconnect this generator, this mode almost disappear, which means this mode has a lot of contribution to the composition of the mode. But it doesn't mean this state variable has large mode shape, because it may not be very visible. Okay, mode shape means this state variable may not contribute to the mode. If you disconnect this element, the mode is still there. But if you place sensor at that variable, that give you a very clear picture about this mode. Participation factor is actually measure both connections, both ways. And it is a dimensionless. Why is it dimensionless? Because the matrix of phi, which is the modal matrix, may have some units, physical unit, depending on what units you use for state variable. And the psi is the inverse of phi. So when you multiply the two matrices element by element, that actually cancel all unit. Okay, participation factor doesn't have any unit. It's just a number. And also similarly, because if you can easily prove if you calculate this participation factor for mode I, mode 1, all the factors together will be 1. If you add them together, it will be 1. That one is guaranteed by the assumption like phi is the inverse of psi. So which means if you calculate participation factor for all state variable associated with any mode, all the participation factor together will be 1. Okay, so that's very useful for designing control to tell which variable contribute the most to that mode. But some other studies also suggest it's maybe more convenient, we can normalize the participation factor differently by another way. We identify the largest one, and we also make the largest one to be participation factor 1. And the second largest one will be the ratio to this one. That is also very convenient. Okay. All right, so we will use the same the 3-machine system. Here we use a more detailed model with a network from the HB 9-bus 3-machine system. So this system is actually a reduction of the Wissing connection. So we know the system has 2 generators. Okay, so it will have 4 compliance eigenvalues, which means 2 oscillatory modes. I will have 1 mode, and we will call it mode 1. So the mode 1, the eigenvalue will be this one, and if you translate that eigenvalue, the real and imaginary part into a damping ratio, the damping ratio is 2.8%, and frequency is 1.5 Hertz. The second mode has this eigenvalue. The damping ratio is around less than 2%. Frequency is higher, is 2.1 Hertz. So we want to calculate the mode shape, which is the right eigenvector, mode composition, which is the left eigenvector, participation factors for each mode. and also we want to draw the mode shape. Just give you some visual example on why we call it a shape, because it really tells the shape. So here is a table. Okay, so the first column just gave you the mode shape. We separate into the magnitude and angle. So here we utilize the normalization based on the largest element. So you see, so the column will have 1 with magnitude 1, because that's the largest one, which means when you solve the eigenvector, you'll find the largest one and divide each element by the largest one. So the largest one will become 1, the other will be less than 1. Similarly, we do that for mode composition and participation factor. So why do I draw a very solid black line separating the first 2 variable, which is actually with the generator number 1 and from the other 2? Because when we check the mode shape based on the angle, if we see, let's see, we use a frequency. Based on frequency, this angle is 180 degree. Oh, and the frequency of a generator 2 is 0 degree, right? The frequency angle of the mode shape angle of the generator 3 is 0 degree. So which means the generator 2 and 3 stay together, oscillating against the first generator. So if you draw the mode shape, you just draw, so each element is actually 1 entry of that right eigenvector. You make it be a just complex number with that magnitude angle. So you'll draw this needle. So you have the blue one actually about generator 1, and the right and the green ones about the second and third generator. So you see the second, third generator oscillating against the first generator. So if you draw the mode shape on the pole grid, okay, that will be this boundary. So machine 1 will be oscillating against 2 and 3. Similarly, you can create this table for second modes based on the eigenvectors. So this line just indicating, the black line just indicating generator 3 is oscillating against generator 1 and 2. That can be verified by angle, right? Because this angle 180 degree, 180 degree, and 0. Oh, here the angle I use actually from the frequency, but the question asks you to draw the mode shape about rot angle. So we need to pick the angle from, but that will give you a similarly result. Right? So if we use the rot angle, so we need to check this angle, that angle, right? So that's why this angle, which means this angle is 88 degree. This angle is a negative 91 degree. Similarly, for second mode, we check the angle 88, and the negative 91. So it will be this mode shape. Okay, for this case, generator 3 oscillating against the other 2. So it will be this boundary. Okay, so there will be a homework. You need to draw the mode shapes, composition, and participation factor for the 3 machine system. All right, so next, I want to talk about 2 methods for modal analysis. We know if you know the model, you know exactly the accurate model, and you can definitely do the eigenanalysis on the matrix A. You can get the eigenvector, eigenvalues, and just analyze the stability. But there could be other cases you don't have the accurate model. The system is too large, or maybe some of the component, for instance, it could be just made by some manufacturers, and they don't give you the detailed model, or even the model is available, you cannot hardly do a linearization. So you have to rely on some memory-based approach. Memory-based approach means you can collect some signals or data at locations, but you still can obtain the results for modal analysis. For the first approach, that would be same as what we talked about. We find eigenvalues, eigenvectors, and then we calculate mode shape, composition, and partition factors. The final answer will be we know for any output. Output here is based on what you really want to study. So the Y here may not be state variable. It can be voltage, can be current, it can be other variable. You really care about its oscillation. So depending on the channel from state variable to the output, and you will have the output will be calculated by this expression. Say here is about the channel, and phi here is just eigenvector. And Zi is a excitation of each mode, depend on phi. If we take a measurement-based approach, we need to utilize signal processing and decomposition to identify a set of damped oscillates, sinusoids. A sinusoid will give you the decaying factor, which is the sigma, and the frequency omega, and also there can be some phasing, which can be characterized by phi. So you want to find a number of damped sinusoid until they together can make up the signal, or the signal can take a majority of the signal. So what you need to do is to find approximation of the measurement signal by using many damped sinusoids, and so each one in the complex domain, each one will represent some decaying exponential function, and the magnitude will give you the amplitude of oscillation and also phasing. And the exponential function will basically tell you the eigenvalue, which is the mode. So if you compare this side and this side, they actually has very clear connection, which means from the model-based approach, you can get the result from a measurement-based approach. And if you have enough measurement, you can also get similar result to the model-based approach. I'm going to talk about the one measurement-based method because this one will be utilized in the project, which is Brownian analysis. I only just use one slide to talk about this idea very briefly. You can definitely find that paper about this Brownian analysis to give you a more detailed algorithm. You can easily find a lot of toolbars which can do the Brownian analysis. So assume you have data from measurements. The data can be collected at many different locations. Assume we can pick just data at one location, we call it J's location, and for a long enough time window. Okay, the time window need to be long enough to be longer than much longer than the period of even the slowest mode. So if this study is for power system, if the slowest mode is 0.2 hertz, you need to 5 seconds to capture 1 cycle of oscillation. So you need to have a number of 5 seconds, maybe 10 or 20 seconds to safely capture that mode. So the capital T here has to be long enough. And you can assume some sampling frequency, determine the total number of samples over this time window. So which means you are going to sample data at the intervals of TS. TS here is just T divided by N. N can be a very large number. Then you get measurement data at those sampling points, right? You have N sampling points for this data. Because you don't know how many modes the system has. The system, if it's too large, they have a huge number of modes. But usually you only care about the top modes, which are really dominant in the data. So you can select a P. P here doesn't have to be close to the dimension of the system. It can be a small number, like even less than 10, and maybe it may be fine. It just captures the most dominant modes. All right, so you can assume the measurement data can be constructed by the P modes. So each mode will have amplitude bi and also the exponential function about some complex eigenvalue, which correspond to this damped sinusoid. Because we can use the variable z to categorize each mode, so in the complex domain, we can just treat the data will be just the magnitude bi multiplied by, let's say, and k here because that's for the case interval. So the problem is to estimate all complex numbers b and z because the number of equations is n, and the number of real n nodes is 4p. So here it is necessary we have to assume the number of equations is bigger than 4p, which means the interval has to be less than the total period divided by 4p. Okay, because both b and z are complex numbers, and each one has 2 real n nodes. Together we have 4 real n nodes. We need to solve both b and z based on the data of the time window. The first step is we solve the modes, the p modes, by constructing a polynomial equation up to a p-th order. Here we're going to utilize this method, AR method, autoregressive model, up to p-th order. So we want to find this equation. By using this equation, we can solve all the modes. To come up with that equation, we have to throw all the measurement data here. Because here we assume the system behaves as a linear system. So to predict what happened starting from this time point, that for future, we can use past data to construct matrix. And that matrix can help to predict the future step. So system will behave as a linear principle. So by using those equations, we can solve this vector A will give you all the coefficients. Then you can solve this equation for all the z, and each z will give you a lambda. So this is because here. Okay. And next step is we solve all the b coefficients. So we'll list such equations and solve b. Okay. So it'll be n such equations to solve this column b. All right. So if this matrix is non-singular, solving a b vector is very simple. You just calculate the inverse of that matrix. But in reality, even that matrix is not singular. The matrix can be very close to a singular matrix, which means if you solve the eigenvalue or diagonalize this matrix, the smallest eigenvalue is too small. It's almost close to 0. Then if you directly calculate the inverse, that can be hard or introduce some error. So if you utilize the MATLAB function, it will suggest you to solve that vector by using this function. This function will do the pseudo inverse. So what it does, it will instead of directly calculating the inverse of t, it will assume the t can be singular. So it can guarantee this matrix to be non-singular. So it will give you the best estimate of x, which is b vector here. All right. So from this step, we can there will be a very clear connection from b and phi. So actually, we can find the mode shape. So actually, if you normalize those b factors, you will have the mode shape. So last step is you just repeat step 1 and 2 for each location. because here we use K for the indices of state variables. So if you can collect data at different location near a different state variable, you can have those B values after normalization regarding the same mode. It will represent the mode shape. Okay. All right. So here each bits represent the element for each mode, and you repeat this process k times. You have p times k numbers of the B factors. So like for the second location, you will have another B1 until BP, right? This is for second location. Third location, keep doing that, and you compare all the first B1 estimated at different location that have the mode shape. After some normalization, you pick the largest one as the basis, and the other will be divided by the largest one. You will have you'll get the same information here by using the memory-based approach. So you'll have the same information here. Okay, next I want to introduce two very useful concepts. Dominant oscillation paths and center of oscillation. For interior modes, usually that can involve the entire system or large area of system to oscillate together. So it will be very critical for system operators to monitor this mode. If the system is too large, eventually you will see a lot of generator will participate in the oscillation. But here you need to capture two very critical pieces of information. The first is about really the dominant paths involved in this mode. And second, what is really the center of oscillation? Okay. So what do those concepts mean? Let's consider this very simple system. It's just two generators oscillating against each other. So this system, if you do linearization, only just has a single mode, single oscillatory mode. So we can consider this analogy, right? So when it oscillates, right, one case is going up, the other case going down, and there's some central point. That point doesn't move at all. So when you talk about mode shape, we really talk about which side is up, which side is down. Okay, so this entire bar will become the path of oscillation, because that's only path. Because one case is to jump up and the other case will fall down. So that is the energy is actually transfers only through this path. So that's called the oscillation path. So what is oscillation center? Center is really this fixed point. It's really the center. So we can borrow the similar idea to identify the path and the center for the oscillation. Okay, for this system, it's very likely this entire transmission will be the path, and the middle path will be the center. The next, so this is what we assume by this for this very simple system. But if you have a very complex system, how do we know which transmission path is really the oscillation path, which path is really the center? So we have to do some study on this system to really understand what happened at the center and what happened on that path. We need to obtain the mode shape for the network. So here we call it a network mode shape because we want to find out some type of eigenvectors, right eigenvector, not only for state variable, also for all the variables through this entire network. Definitely, if you can make an entire system be dynamic, be some model by differential equation, you just do a similar study, you can have mode shape for the entire network, or you can utilize some memory-based approach to estimate the mode shape at different locations. We need to find the mode shape about this frequency, this mode, depending on which mode. So which means you can do such study for any frequency. So we'll look into the line currents, bus voltage, magnitude, and bus voltage phase angles. We only pay attention to those variables to find out their mode shape above this frequency. If we use a membrane-based approach, those mode shape can be estimated by, for instance, Brownian analysis. So you can collect data at different locations to measure either line current or voltage magnitude or voltage angle, and you construct those B1, B2, B3, right? And at different locations, you will have mode shape. So usually it's just in order to find the mode shape only for that frequency, you can utilize some measures such as the power spectral density, and basically just tell the magnitude of that mode. You can see from the data, from the signal. Usually you need to utilize Fourier transform. So you can collect data in the time domain through the Fourier transform. You identify the value, the power spectral density at a certain frequency, and use those values to construct your mode shape. So those are the definition of power spectral density. Dominant oscillation path is the transmission path along which the line current magnitude has the largest variations associated with the mode. So to identify the oscillation path, you need to find line current data and find the mode shape and power spectral density. And they have larger variation than other paths, any other path. So that path will be the dominant path regarding this mode. The center of oscillation in the bus on the dominant oscillation path. So first it has to be on the path. And it has the largest variation in voltage magnitude and the smallest variation in voltage angle regarding that mode. Okay, so what does this one mean? So the oscillation center has largest variation, so which is like in this supporting point. So that point will be subjected to the largest force. So the force can be analogy to the voltage variation. The smallest variation in the angle, because this point doesn't move at all. Okay, so let's go to this simple network model. I borrowed this one from that book. You can find that the whole chapter gave a lot of useful studies, including those concepts. So for this system, the first chart is actually the magnitude of mode shape on the voltage variation. So you see the bus 3 had the largest variation. So it studied two different loading conditions, both confirm the bus 3, if the two generators oscillate, the bus 3 will have largest voltage variation. And how about the angle variation? The smallest angle variation also bus 3. The bus 3 doesn't change the phase. So that confirms this is the oscillation center. Because for this system, we only have a single path. If you have a mesh network, you need to also check the line current variations that tell you where the path is. So this one is explaining why from our early case on the 3-machine system, we see actually one side is oscillating against the other side. But here we only just check a 3 generator. If you're able to calculate line currents, bus voltages along all the paths, you'll be able to identify probably maybe a center. Okay, maybe a center from somewhere. I don't know. That line doesn't tell you the accurate center, but you can, if you want, you can utilize this model to check where exactly that center is. But we'll be around this cassette. And the other mode will have another oscillation center. Oscillation path will be the one path. I don't know. It can be this path. This has largest current variation. Okay. So which means to understand this mode, this path and that center will be most critical for you to either place sensors or do control to mitigate that oscillation. To give you another example, on mesh network, which is a ECE522 bus system, which model entire Wi-Fi connection. This was done by one of my past students. So because for this system, the engineer really worry about this inter-area mode. That actually involved the Oregon state oscillating against California. So that actually happened in a number of the large events in Western connection. So if you have a disturbance in that area, that will cause the north system, north region oscillating against the rest of the south region. And for this case, the oscillation path will be this path. That will have largest current variation. And oscillation center is actually on that point. So that one is confirmed by the mode shape, the magnitude of mode shape on the bus voltages. So that actually indicates that point will have largest voltage variation and has smallest angle variation. Okay, so next we talk about what can we do with oscillations. We already covered about how to utilize PSS to improve damping, but the idea here is to first compensate the phase lag of a excitation system, and then you introduce additional gain. That one will give you additional damping. But the PSS is actually utilized as generators with the excitation system. We can also improve dampings through HVDC converters or fast devices such as SVC. SVC is mainly used for voltage control to provide dynamic reactive power, but it can also provide damping. So the idea is very simple. Because for this case, if there's any short circuit, that short circuit will cause oscillation, right? So you'll see largest voltage variation at bus 3. If I have SVC placed on bus 3, the SVC doesn't know what happened on the generator, but the SVC only believe, okay, you have some voltage event. You cause this bus 3 to vary a lot. So I will give you ready power. I will mitigate this the voltage variation. So if you make this voltage variation smaller, that also reduce the oscillation. Even it's not straightforward, but it will give you a positive effect on the damping. And also you can utilize some supplementary control. Similarly to the PSS, you can bring a remote signal to give you the best control on the damping. How do you place SVC? If you only have a single SVC, that one will try to mitigate the voltage variation. You definitely need to place on the dominant oscillation path and on the center of oscillation, similar to the two generator case. Okay, you put single SVC there, that it will improve damping. But if you have a very large complex system, SVC need to be placed at the bus where voltage swing is most sensitive to the susceptent chain. Basically, that means it has largest voltage participation factor. I will explain this one a little bit in the last session about voltage stability. But basically, it's also a type of participation factor describing how this SVC can participate in mitigating that variation of voltage. You can read that chapter, so that cover everything. But here I only just use a couple of slides to quickly highlight some useful method. Let's talk about controllability and observability of a mode. Okay. So this is our linearized model of a regional system. So here I add two things. The first is the input. Because earlier we only just talk about the zero input response, but here we want to study how to control the oscillations. So we need to provide a channel for that U to provide control to mitigate oscillation or improve damping. And also, if we will not be able to measure the state variable directly, we also need to design some sensing channel, measurement channel. So the measurement data will not be state variable, will be the Y collected from the channel. Okay, so definitely there can be also the impact from the input to the output. So this will be the general linearized system model. Okay, but this is not convenient to study how to improve the small signal stability. We'll borrow the similar idea from the zero input response to find the eigenvector. So if we're able to transform original state vector to the new state vector, the fully decoupled, we just replace delta S by phi Z here, okay? And so we'll generate the second set of equations. So in the second set of equation, so this one just diagonalize A matrix. And this one, the phi aside here is just inverse of phi. But because both sides multiply the phi inverse. Okay. And then it will give us the first differential equation will be only about the decoupled the mode, the state variable Z. So we need to focus on design about this B prime, not the original B. The B prime here is just the matrix from the left eigenvector multiplying original B matrix. And also the input, the measurement data need to focus on this C prime. Okay. So we call the B prime matrix as the mode controllability matrix. That is related to mode compositions. Because that matrix is simply just a regional control channel transformed by the matrix about mode composition. So this B prime just tell you really the controllability for the mode from those input. So if one row of the B prime is 0, which means that input has no control effect on the mode. So we definitely don't want any row of B to be 0, unless you want to avoid that control. Okay. And the mode observability matrix will be just C prime, right? Because that's related to the mode shape matrix. If one element is 0, which means that mode is not observable from the measurement data. So just make it simple, we consider there's only just single input and single measurement data, which is single output and also single input, single control signal. So B here is just one column vector and C is just a row vector. Okay, so we can get transfer function from the input to output. So I assume you know how to do it. So finally, it will be summation of many such first order system. So each first order system is related to one single mode. And we call this Ri as a residue. Residue is just somehow can be understood by the multiplication of observability and controllability. So which means if you make this Ri bigger, this mode will have more participation from the input to the output channel. But that need to have either observability to be large enough or controllability to be large enough, or both to be large. And this Ri is exactly participation factor. Okay, if the case element of a C and B is not 0, only that one is not 0. For instance, if like K be 1, we'll make only the first element, first control output channel to be non-zero, first input channel to be non-zero. So this residue is exactly participation factor, which means we can utilize participation factor to design the control. So the method will be, if I have only just local control, I need to place the controller where the participation factor is large. So it will guarantee to have overall observability, controllability to be not small. If I can do remote control, which means I will collect memory data at one location and add control signal at another location. So when I place a controller, I need to make the controllability to be large. When I place sensor, I need to make observability to be large. I need to probably select B and C to make both be large. All right. So when I collect the remote signal and send it back to the controller, I can design a transfer function as feedback control. So this transfer function need to, if I'm able to design this H, I can design the target eigenvalue, including how I want this frequency to shape, how I want the damping to be improved. Because the closed loop transfer function will be this one. The G here will be original transfer function from that input to that output from the original system. And the new closed loop transfer function will have this one. So denominator will be the characteristic equation. So if I make denominator to have the design eigenvalue, I only just need to make this one to be equal to -1 over G. G here, lambda 0 is just design eigenvalue. Okay, so if I'm able to estimate this transfer function by using this formula, I will know how to design this H. That H need to be able to add the affection on the design eigenvalue. So this is my last slide. I only just integrate everything into one slide, just give you the high picture of the main idea, but you really need to read about this chapter. For the two-error system, Quinter two-error system, if there's any fault, that will cause inter-error oscillation between error 1 versus error 2. For this case, if you have no control, and the oscillation can become unstable. It starts from a small signal stability. It's growing oscillation, but eventually become transient instability. Okay, we don't have to design transient stability controller. We can just improve damping to make if this oscillation smaller, and finally the system can become stable. So we can add damping controller. The damping controller here is SVC. So first we place SVC at bus 8 based on the detailed study from the Quinter's book. It tells the bus 8 has a good mode controllability and the bus participation factor. Okay, so even without any remote control, this single SVC can improve damping. So it's also near the center of oscillation. So I assume we just put that SVC there. If we want to add a remote signal, we'll take the input from a remote location, delta Y. So we take it from,